Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will go through everything covered in week 2. So we just looked at graphing logarithmic functions and differentiating logs. So use these notes here to help you graph log functions of this form here. So log functions always have a vertical asymptote. It's the negative of whatever number is in the brackets. They always have an x-intercept, which you can find by letting y equal 0. Sometimes they'll have a y-intercept, and if they do, you find it by letting x equal 0. So when you're graphing, mark the asymptote, mark any intercepts it has, then mark one more point, and then note that it tapers off. So what do I mean by tapering off? Well, let's look at just the graph of y equals log a to the x. So if a is greater than 1, it's an increasing function that looks like this. So it's increasing quickly, and then it slows down. It increases at a decreasing rate. It tapers off and goes on like that forever. So if a is between 0 and 1, note a is never negative, then it will sort of be the opposite. It's decreasing function and it still tapers off but in the other direction. So note when I say increasing, it means that if x gets larger, so too y gets larger. But if a is between 0 and 1, as x gets larger, y actually gets smaller. So log graphs either take that shape or that shape, depending on the value of the base. All right, let's look at this example here that will hopefully make things clearer. So to graph this, I'm going to make it easier on myself. This too can be moved to the front, remembering that is the third log law. So I'm going to remove it from the power up here. So we'll start with the vertical asymptote. So here b is 1. The vertical asymptote occurs at x equals minus 1. So let's look at why there is a vertical asymptote. So if you have something like log a of x, that's saying to what power do I raise a to get x? Now, if a is a positive number, you can't raise it to any power to get an answer of 0. You can't raise it to any power to get a negative number. So for example, 2. You can't raise 2 to any power to get 0. You can't raise 2 to anything to get a negative number. So whenever you're graphing a function of this form, the brackets here must always be positive, greater than 0. And that's the same here. The brackets must be positive because I'm saying 3 to the power of what gives me this. You can't raise 3 to any power to get an answer of 0, so x plus 1 has to be greater than 0, x has to be greater than minus 1. So remember, an asymptote is like a no-go zone. The graph will never hit this line, it will get closer and closer to it, but never actually hit it. All right, let's look at the x-intercept. There is always an x-intercept. If we let y equal 0, we get 0 equals 2 log 3 of x plus 1 minus 2. So let's just quickly solve this. So we're going to add 2 to both sides to get rid of it there. So I get 2 log base 3 of x plus 1. Then I'm going to divide each side by 2. I get 1 is equal to log 3 of x plus 1. How do I solve this? Well, this just means that 3 to the power of 1, which is 3, must equal x plus 1. So it turns out x equals 2. So that means the x-intercept occurs at x equals 2, which is there. So what about the y-intercept? Well, this one will have a y-intercept because this plus 1 here has shifted the graph left. So to find the y-intercept is pretty easy. You just let x equal 0 and put this in your calculator. So log 3 of 1 is 0. So the y-intercept is just 0 minus 2, which is negative 2. So I found the asymptote and the intercepts. To make it easy on myself, the next point I find I want x and y coordinates to be whole numbers. So I'm going to put a number in here so that this is a power of 3. So if I put x equals 8, I get 9 here, which is a power of 3. So if x equals 8, I have 2 log 3 of 9 minus 2. Log 3 of 9 is 2. 2 times 2 is 4, minus 2 is 2. This actually goes through the point 8, 2. And from here, we can sort of see the shape of the graph. It's going to go like this. Increase at a decreasing rate, and you can see that it tapers off, and we're done. All right, let's look at some calculus with logs. So it turns out to differentiate using logs, you only need two rules. Derivative of natural log of x is just 1 on x, and the derivative of the natural log of some function of x, you just differentiate the function on top and write the function on the bottom. So let's make this clearer using an example. So let's say, for example, I have y equals natural log of x squared plus 1, and I want to differentiate that. So all I need to do is put the derivative of what's in the brackets on top. So derivative of x squared plus 1 is just 2x. And then I put what's in the brackets on the bottom. There you go. I'm done. What about if I wanted to differentiate the natural log of x plus 4 cubed? Well, remember, I can use the log laws to move the 3 to the front. This is just 3 ln x plus 4. So the way I'm going to differentiate this, I'm going to differentiate this and just multiply it by 3. So the derivative of natural log of x plus 4, so I'm going to put the x plus 4 on the bottom, and I'm going to put its derivative on top. The derivative of x plus 4 is 1, and then multiplying that by 3, I just get 3 over x plus 4. And I'm done. So it turns out we can use this to differentiate functions of the form y equals a to the power of x. So how do we do that? We're actually going to write it as e to the power of the natural log of a to the power of x. See, the way we differentiate e's, remember, is we keep the e and the power the same, and we multiply by the derivative of the power. So what is the derivative of ln a to the x? Well, remember, of course, I can write ln a to the x as x ln a, because I can just move this second power to the front. So the derivative of x ln a is just ln a. So I've got y dash equals ln a, e to the power of ln of this. So that, remember, this just equals a to the power of x. So the derivative is just ln a times a to the power of x. So for example, if I had y equals 2 to the power of x, its derivative is just ln 2 times 2 to the power of x. Predictably, derivative of 5 to the power of x is just natural log of 5 times 5 to the power of x. So how would I differentiate logs with a different base than e? Well, if I want to differentiate this, I really only know how to differentiate when it's base e, so I'm going to use the change of base formula. So the change of base formula would have log base e of x on top and log base e of a on the bottom. So remember, this is just ln x. So the way I differentiate ln x over ln a, where a is a constant, is just going to be 1 on x again, but this time I'm going to multiply by ln a. All I did to get from here to here was I just made this 1 on x, and I kept the ln a on the bottom. So for example, if you want to differentiate y equals log base 3 of x, it's just going to be 1 on x times ln 3. If you wanted to differentiate log base 5 of x, it'd just be 1 on x times ln 5, and so on. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.